class today. I record everything in lecture. Everything that gets said or written on the screen that you see is recorded and gets posted to YouTube. Okay? I will deposit those lecture videos to a module within Canvas. Okay? They are also available on YouTube if you don't want to go through Canvas. If you do a Google or a YouTube search for the channel CGC Chem Mike, every lecture I've ever given at Chandler Gilbert is deposited there, every single one. Old semesters of 236, 260 for biochem, all of that's up there available if you want to go through and do it. Okay. Just like in lecture, if I ask a question, like say, what's my name? And there was that long pause is recorded into the video. There's no post-editing to any of this. Okay. I did see, I thought that you could speed things up in YouTube, so you can go at like double speed maybe, and that can help you get through some of those long pauses. Okay. And it'll be more entertaining. Play pause it is a slightly different system because nobody watches the videos. Okay, or at least very few people watch them, particularly if I build a video specifically for class that I want you to watch ahead of class. I get very few people watching it and very few people understanding what's happening within it. So what Play Pause It is I can now take that video and I can upload it into Play Pause It, and every 2 or 3 minutes I can ask a question. So when I'm asking a vague question in the video, okay, and then give you the answer right away, I can ask a vague question that you have to answer before the video continues playing. Okay, so it should help keep you accountable and help you kind of moving through it. I'm also using bookmarks in the YouTube video so you can kind of skip to different sections on non-lecture recordings. Okay. So the big one for that is the Diels-Alder reaction. Okay, I was holding off on posting that video intentionally because I didn't want to give away answers for the lab. Sorry for those people in the lab. Okay, but that video is now posted. It's got a bunch of questions in it. Some people have looked at it. Some people seem to say it's useful. Okay. To those some people, you're good people. Well, the people that didn't think it was useful, well, tough. Okay, you can talk to me and we'll work through it. General questions about anything that was covered by Brian you want me to double back to?
Not about Brian, but how many Diels-Alder videos did you post?
There are 2 Diels-Alder videos. There's the first one that was intentionally for lab, which just set up the basics of the Diels-Alder for lab, but it really gives no answers. And then there's a Diels-Alder follow-up that gives all of the answers for what Diels-Alder is. So if you're not in the lab, the only one that's posted to the lecture site is the Diels-Alder with all the answers in it. If you're in the lab, you have 2 videos that you have access to. Okay? When it comes to Play Pause It, the other thing is I can go back and I can look at who's answered questions and I can see how you're doing on those questions. So before lecture, I can look at it and say, you don't understand this, this, this. Okay, we're going to talk about those 3 things and not talk about all the stuff that you guys already knew. Okay? So I can use that information. If you don't do it, I can't use that information, and you're just getting random me talking for 75 minutes. Okay? Or longer if you don't pay attention to the clock. Okay? That was supposed to be kind of funny. Thanks for like 2 of you to laugh. For those of you who don't know me, I am very available. You can talk to your classmates. Hopefully they've kind of stepped in and told you some information. Super available in office hours. I highly encourage that. I watch email fairly frequently. Please contact me. Let me know that something's going on, and I will try and help you as best I can. Okay? And usually relatively quickly on the turnaround. Okay? Though maybe at weird hours. Okay? Homework was officially due last week. Brian didn't know what was going on with it. You didn't know what was going on with it. Don't worry about it. Everybody got credit for the homework last week. Homework is now due next week. So every even week, 2nd week, 4th week, 6th week, 8th week, every even week, you will turn in a homework. Okay? I don't know when Thanksgiving is, but if it's on an even week, you're turning in a homework that week. Okay? It is officially due Friday by 5 p.m. You can turn it in class, or you can take a picture of it and send it to me via an email. I'll mark it. All I'm doing with the paper homework, just looking at it and saying, yep, you wrote something down. Okay? So that is still going to be an important aspect, is writing stuff down. The other big aspect with homework is there is still online homework. Okay? The online homework is a little bit more pointed. Okay? It's more directed, and you get instant feedback on it, whether you were right or wrong. For those of you that had me already are probably aware of the three wrong answer rule. Okay? Those of you who haven't had me, okay, or haven't had this homework system, you get 3 wrong answers. At 3 wrong answers, you stop putting in answers, and you send me an email. You are either missing a concept, or there is a typo within the question that needs to be addressed. Okay? You start answering more than 3 times, what ends up happening is you get increasingly more frustrated, and you can end up answering it increasingly more times, which then also removes more and more points. Okay? At 3 attempts, you've lost 15% of the credit for that one question. That's not that big of a deal. Okay? And if I can help you, that's all you've lost is that 15%. Okay? Which, when we look at grades, when it comes to homework, the scaling on the grades is 90% of the points. Okay? So the homework is there to give you that practice and force you to use it. That's why the points are there. It's not there to take points away. Okay? So please don't go clicking through it like crazy. Okay? Everybody in the classroom, I'm trying to now force you to get together and talk to each other for a very good reason. The more you talk to each other, the better you will do in this class. Guaranteed. Okay? So try to talk to people, talk about the material, how to get through it, what you need to do. Make sense? Questions? Yes?
Like all the review questions, is that graded? Like, do we have to do all of them before?
Good point. On the online homework, there's that review section. So we can put a couple things to a vote here. Number 1, all of those review questions are exactly that, review. There's no grade associated whatsoever. I had some people from the spring semester that wanted practice over the summer, so I made sure to put that up so that if someone signed in early, they could work through practice questions. That's it.
Will it stay there like the whole semester?
They will stay there the whole semester, which brings up the next question. Do you want the review questions at the top of the list or at the bottom of the list? I'm here in the bottom. So I will put the actual questions that are more important to be done for the credit up at the top, and I'll shift the review questions to the bottom. Yes?
The written homework, 10 questions or 20 questions?
What's the vote?
Syllabus says 20, roughly 20.
Okay. What's your vote?
I count A, B, C.
10 per week. So we're still going at 20, so 10 per week. And so this is the other thing that people tend to panic about and go, oh, 20 questions is a lot on top of the online homework. The online homework, how much are you writing? Theoretically, you are writing it down because answering it in the online system is pointless if you aren't writing it down, because that defeats the point of doing the homework, is getting the muscle memory of drawing the reactions. Okay? So as you're doing the online homework, you're writing stuff down. Well, the online homework has probably more than 20 questions every 2 weeks, which then means the work that you just wrote down, you turn in. Perfectly all right with that. Okay. So the handwritten homework is just that. It's proving that you've been handwriting work. What you do for those questions, really could not care less. Okay. You could even do general chemistry questions. I probably would still give you credit. Okay. That's not good for you, but I would probably still give you credit. I just want to see that you're writing something.
Last semester, Mike, suggested homework problems from the textbook.
I haven't posted that yet, have I?
Post that when you
I will post. I've got a file from from the Cardi textbook where I went through and said these questions I think are important. I'll post that so you can do that as suggested homework. Okay. The other option you have, the practice exams. I've posted all of the old exams. You've got access to those. You can do those as practice for the paper turn-in homework. Okay.
So recommend the ACS book.
The final for this class is the 1-year ACS exam. For those of you who have not taken an ACS exam, the average is 50%. Okay? It is a stupidly hard exam. Okay? It gets normalized, so don't freak out. A 50% is a passing grade. Okay? That is what average means. Okay? So it'll get normalized and adjusted. If you get, say, an 80th percentile on the exam, you are 3 standard deviations above the average. Well, 3 standard deviations above a C is an A. Okay? So if you get an 80 or 90% on the final, That translates to nearly a perfect exam score, which really boosts your grade. If you're lower than the average, that's when things start to become kind of questionable and not a good place to be. Last year, the average for the entire class was the 80th percentile. Okay? I want to continue to see that trend. So, what's that? That was no fall semester for the whole year. The half semester exam is a little bit questionable to use as a gauge. But the whole year semester exam, or the whole year exam, the average was the 80th percentile for the entire class. Okay? Which then translated to, I think we had 14 people in the class, 13 A's and a B. Okay? Because they proved that they knew the material on that final. Okay? So it can really bump your grade if you prepared for that exam. That's why the ACS study guide is very helpful, because it gets you that same format. When it comes to our in-class exams, I still build questions based off the ACS study guide. I still build them in that same kind of tricky, obnoxious format that you see on the ACS final. Okay? So take advantage of those as practice. It'll help out in the long run. Okay?
There's only one, right? So like
There's only one ACS study guide. Yeah. Yep. Except now it's the whole book. Yep. Okay, and since you asked that, we can do a couple things. Organic chemistry. Okay, how many semester course is it? Wrong, it's a 1-year course. Okay, it is a 1-year course that we broke into 2 semesters. Okay, so if you spent first semester memorizing the material for exam 1, probably wasn't that big of a deal. Then you had to memorize the material for exam 2 and exam 1, because it continues to build. That became a little bit more difficult. And then exam 3 became even more difficult. And the final became even more difficult. Guess what our first exam is? A test on current second semester material and everything from first semester. It stacks. Okay? So you need to start working on not just a rote memorization, which is the standard format for the class, but understanding how and why the reactions work. Looking at mechanisms and looking at the balances of charges. Okay? Those of you in the lab, you should already be having an experience with this because you saw that with the Diels-Alder reaction. Okay? That's how that lab is designed, is forcing you to look at the dynamics of how the reaction works, not just saying it does work. Okay? Other questions? Okay. A couple things I'll address here. Number one, yes, I saw the typo. Actually, no, I didn't see the typo. So somehow or another I posted something wrong. For the dialogues, if you're going to use the dialogues, that's the subject line. D FA16 CHM236, not SP. What does SP mean? Spring. We're not in the spring. Okay, it's a copy and paste issue. You should be using FA. If you use that subject line, you should get an auto response from me saying, hey, you submitted the dialogue, thanks for doing that. If you hear another response from me, that's bad. Okay. For those of you that submitted with the spring subject line, don't stress about it. Now, please just start switching to the fall subject line and everything will be fine. I will take anything that was marked as spring and put it into the fall one. Okay, other questions? Okay, one of the very first quiz questions was, what are the 5 reaction types? I'm kind of suspicious that Google was used because we got combination, decomposition, composition, or whatever that is, combustion, single replacement, double replacement. These are 5 reaction types. These are the 5 reaction types that you find in general chemistry. Fun thing about this class, not general chemistry. What are the 5 reaction types we're looking for? For those of you that were in the tutoring center before class, do not answer. 5 reaction types for organic chemistry. Substitution. Okay, we got substitution. We have our elimination. I think I heard someone say addition. 3. Acid-base. Probably the potentially easiest one. And for those of you that haven't had me before, when I say acid-base, which type of acid-base am I referring to? Those of you who had me, Which acid base am I referring to? This could be a long semester, guys. Bronsted-Lowry is our acid base when we're referring to that. I don't use Lewis. Why? The whole point of the Lewis definition was to apply to all reactions. So if I call acid base as Lewis, guess what addition is? Acid base. What is elimination? Acid base. Substitution is acid base. So when we're talking about acid-base reactions, when I reference acid or base in a reaction, I'm referring to the Bronsted-Lowry definition. Okay? Because the Lewis definition applies even to the Bronsted-Lowry, I don't use Lewis at all. Okay? Because it's too broad. It applies to everything. What do I use instead of Lewis acid and Lewis base? I use nucleophile and electrophile. The Lewis acid is the, I will fully admit I have a hard time nailing this down. So Lewis acid, I have a hard time with that, so I compare that back to Bronsted acid, because a Lewis acid is a Bronsted acid. What is a Bronsted acid?
It's an electric.
True, but stop using fancy words. Okay, Bronsted-Lowry acid. Give me an example of a Bronsted-Lowry acid. Any Bronsted-Lowry acid. Well, those aren't actual molecules. Proton, hydrogen, not an actual molecule. Give me a molecule of a Bronsted-Lowry acid. HCl, hydrochloric acid. What makes hydrochloric acid dangerous? It dissociates completely to give us H plus and Cl minus, which is the reactive dangerous one. H plus. So if a Bronsted-Lowry acid has H plus, what does the Lewis acid need to have? Positive. If it is positive, does that make it a nucleophile or an electrophile? An electrophile, because what does the positive charge want? Electrons. It is electron loving. There's our electrophile. Once one is nailed down, what naturally happens with the other? It then has to be the opposite. It'll be negative, which then means it is a nucleophile. I do happen to be one of very few instructors that ignore the Lewis definition. I was just at a conference with organic chemistry and everybody loved the Lewis definition. I think it's a horrible definition to use. Okay? Useful, just not good. So acid base, we got 4 up there and we're missing the 5th one. Use a different hint. The Ninja Turtles might say this. Yeah, there we go. Our radical reactions. When you're looking for your reagents, you should be classing them according to any one of those 5. Those are going to be our bulk kind of classifications. We have subdivisions in those, getting us our mechanism, how each of those reactions occurred. Okay? And so we will be spending a lot of time on mechanism, but if you can at least nail down your reactions and do some of the classifications, that can help you with your synthesis. Okay? Ow. So there are all our reactions. So, because you didn't have any questions about the old stuff, at least yet, okay, we'll move on to the new stuff, which is now Chapter 10. Chapter 10 is looking at useful substitution and elimination reactions. Okay. It's kind of a weird chapter because it's a hodgepodge, if you're not using our textbook, of reactions from a bunch of other sections. Okay, so I decided to group that chapter down into these subsections. We're making better leaving groups of oxygen. That's 10.1. Okay, and then we're making better nucleophiles and leaving groups. And that gets us our epoxides and technically oxetanes. But we'll really only focus on the epoxides. That's section 10.6 to 7. The amines and our substitution. So looking at nitrogen being involved in our substitution reactions. That's 10.2. We'll look at nitrogen when it's involved in elimination. 10.8, 10.9. And then how can we make other nucleophiles? This is an interesting one. We're making what a nucleophile? carbon, what was a nucleophile? An electron donor was our nucleophile. What characteristic would we expect of a species that would donate electrons? It has electrons. What kind of a species would have electrons? Have electrons. A cation is positive, so it actually doesn't have any electrons. So what species has electrons? So we could say anions. Okay, what would be a characteristic of an anion? Negative. Why is it negative, though? Lone pairs. Where is it getting those electrons from? From something else. Why is it getting those electrons from someplace else? Why is that atom getting those electrons? Electronegativity. So stability is ultimately our biggest answer to it, but it's too general. It's electronegativity. The more electronegative atom we have, the more likely it has electrons, which means the more likely it can act as a nucleophile. Where did we start? Oxygen. What's special about oxygen? It's the second most electronegative element on the periodic table. Okay, it has tons of electrons. Next one was, in our amines, we have nitrogen. Nitrogen's the third most electronegative element on our periodic table. Okay, of course it's going to have more electrons. Why is it weird when we jump to make better nucleophiles and we're now looking at carbon? What can you tell me about carbon? It does not like holding electrons. It's not very electronegative. We very rarely see it with a negative charge. Okay? That's what makes that section very important, because what we're looking at is making carbon a nucleophile, and that is not easy. Okay? It happens so rarely that most of those reactions get rubber stamped with the person's name that discovered it. That's why most, or at least I, didn't like those reactions. They go, what's the product of a Grignard reaction? I don't know, who's Grignard? Tell me what I'm looking at for a reagent and I can work with it. Okay? So realize that we'll run into a lot of named reactions through that system. Okay? So, oxygen and substitution and elimination. So we've got a general structure here. What functional group are we looking at? Okay, we have an alcohol because we see, do not accept that you see an OH. You have a COH. Okay, we have to include that C in there, and in particular the sp3 hybridized C, because if that C happened to have, I don't know, another doubly bonded oxygen to it, do we have an alcohol? No, we'd end up with carboxylic acid. Okay? So we have to be careful when we're looking at our functional groups to make sure we qualify them correctly. So we have an alcohol to start this off with. Okay? Oxygen is synthetically useful because of its lone pairs, okay? Which makes it act as what? Nucleophile. Okay? That can now make this structure be a nucleophile, because what can those lone pairs do? They can donate electrons. And we now have a nucleophile. Cool. So we've got some reactivity there. Okay. Oxygen is also synthetically useful because of its electronegativity. What is that one referencing? It's taking electrons. Where is it taking electrons from? Everything. So let's get more specific when we look at this structure. It can take it from the carbon. What happens when the oxygen takes the electrons from the carbon? Yeah, it can break the bond, potentially, before we even break the bond. That carbon becomes partially positive. With it being partially positive, what do we now have? Yes, we have reactivity. How is it reactive? We now have an electrophile. So recognizing the patterns in what we've got sets us up. What else? Where else could it steal electrons from? From the hydrogen. Still connected to a hydrogen, so let's say it steals electrons from that hydrogen due to its electronegativity. What happened? When it stole electrons from the carbon, we had a positive carbon. What do we have if it steals electrons from the hydrogen? We have a partial positive hydrogen, meaning we have our Bronsted acid, because it can now donate that hydrogen to a different structure. So looking at our compound and seeing the differences in electronegativity, okay, and lone pair activity allows us to come up with predictions on how our potential reagent can go through and react. Okay? For all of those same reasons, it can be bad. Why can it be bad?
What do you mean by bad? Like, blow up bad?
You already knew that from me, because you already had me before. Vague questions. Deal with it.
How is the oxygen there?
So why is the alcohol functional group now potentially bad? So blow up bad, that's not a bad idea. Ethanol, does it blow up? It's flammable, but it doesn't blow up. So blow up bad, no. Try again.
Well, the alcohol, the OH specifically is a bad leaving group.
So we could reference it as a bad leaving group, which then minimizes the activity of it being a good electrophile. Okay? Because if the OH can't leave, we can't have the electrophile exist. When you run a reaction, how many products do you want?
One.
Why?
Because the more products you have, the more complicated it gets and dangerous it can
Your
be.
yield becomes crappy. The amount of time you spend in lab becomes longer. Your life starts to suck more and more because all you're doing is spending time in the lab. What is the problem with this alcohol functional group? How many sites of reactivity do we have? 3. We had the nucleophile, we had the electrophile, and we had the Bronsted acid. I didn't copy that up higher, sorry. Okay. So we have 3 sites of reactivity. When I mix an alcohol into a solution, what can that alcohol now do? 3 freaking different things, getting me potentially 3 different products. That sucks when it comes to synthetically. Okay? So when we're looking at the alcohol functional group, we need to be thinking about both what it can do, okay, to get to where we want to, but then also think about, well, crap, it could also do this to take me away from it. Okay? When we looked in first semester, when we ran a reaction, there was typically only one thing that could happen. You did a substitution. Done. You did an elimination. Done. Second semester, it's you can do the substitution or the elimination or the addition. What conditions are going to set you up to get to each of those positions? So you have to be thinking about and looking at all of those possibilities and recognizing the patterns. Early on, you may not see those right away. That's fine. That's what practice is for, okay? To help you recognize when it works best. Make sense? Okay. So, oxygen is problematic, so I want to change it. Okay. I want to turn it into something that is less reactive. So on the left-hand side, what did I turn it into? Halogens. Okay. Why would I turn it into a halogen, or technically a halide? Okay. Specificity. What was I hearing down here?
Good leaving groups.
Good leaving groups. So we had addressed the issue that oxygen, that OH, is a bad leaving group. If I convert it to a halide, what have I done? Those are really good leaving groups. What else have I done? Where's the reactivity in the halide? Just the carbon. It is now just an electrophile. I took a structure that had 3 sites of reactivity, one of them not so great, and I now changed it to a new compound. In the process of changing it to a new compound, I enhanced the reactivity of one so much so that the other 2 disappeared, okay? And I enhanced it. So that kind of comes at one thing. We enhance the reactivity of one by making it a better leaving group. So how do we go through and do that? Well, that's where the reagents come in. Okay, so part of synthesis is recognizing what you need to do to change it. Okay, we need to minimize some reactivity, or we want only the electrophilic characteristics, so let's turn it into a halide. How do I do that is the reagent. Okay? What are you responsible for in the class? Everything? Really? Sorry? You have to know the reagent, and you have to know what direction you need to be pushing it into. Okay? So that's why we'll try and address both. Knowing the reagents, If that's all the class was, I'm done. Literally, that's it. I'm done. There's nothing for me to do because there's lists of reagents. I can say, here's the list. Talk to me again in 16 weeks. I'll give you a test to see if you know those reagents. Okay? What we are here to discuss is not just the reagents, but how they work, what they are trying to go through and do. Okay? What happens when we move to the right-hand side? What have we done? Okay. Did two different types of reactions, so that's interesting. What is the top right one doing? Top right? Okay, thank you for changing that from addition to substitution. Okay. Remember those 5 reaction types? I guess what I should have mentioned is not only do you need to know that there are 5 reaction types for organic chemistry, but being able to look at a reaction and say, ah, that's an addition. Okay, that's a substitution. If you can't do that, all of this becomes very, very difficult. Okay. Why is this a substitution? Okay. Minimally, I lost an H and I substituted it for this giant freaking carbon chain. Okay. What happened in the bottom case? There we go. Kind of running out of space, and we got our elimination down there. So let's think about why we might do either one of these. Why would we do the substitution? What does this substitution do to the reactivity of my oxygen? Or let's switch it a little bit. What does that substitution do to the reactivity of the alcohol?
We don't have the alcohol anymore.
You don't have, okay.
So
But what did the alcohol do?
it gave us a larger structure, but it
The alcohol wasn't a larger structure. This structure is now larger.
I mean, like the alcohol, we use the alcohol to give us a larger structure.
Okay, how? What were the reactivities of our alcohol? Bronsted-Lowry acid. Do I have an acid anymore? I changed the reactivity of the structure. I removed the acid-base characteristics. If I now dump an alcohol into a base, I expect an acid-base reaction. If I dump that other structure, my substitution product, into an acid or a base, do I get an acid-base reaction? No. Why? It's not an acid anymore. Okay? I've eliminated some of that reactivity. Okay? What other reactivity did our structure have?
And bacteria and carbon.
Okay? We had positive charge on that carbon, meaning it could act as an electrophile. Was the OH a good leaving group? Is the O carbon chain going to be a good leaving group? No, why not? Why are they both bad leaving groups? Yes. What is the leaving group doing? It is taking electrons with it, which means it becomes negatively charged. For it to be a good leaving group, what does it have to do to that negative charge? Make it stable. Is O minus a good leaving group? No. So I don't care what that O minus is attached to, a hydrogen, an R group, something else. That's not a particularly good leaving group because it is charged. Okay? So I still don't have a good leaving group. So it's not very good as an electrophile. It's not very good as an acid or as an acid. What was the last reactivity we had? Nucleophilic characteristics. Taking the oxygen's electrons and doing what with them? Sharing them. Does this new product change that reactivity? How? It's bulkier, which means what? Steric hindrance, which means what? It is not a good nucleophile anymore. We have sterically hindered that structure. Our alcohol could potentially act as a nucleophile. It only has some bulk down here. The hydrogen's tiny. Who cares about it? What happens when we add that other carbon chain? Bulk, and now no reactivity. Alcohol is fairly reactive. What is the new functional group we have generated up there? In the red, yes. We have an ether. What is the reactivity of our ethers? Virtually nothing, which is why ether is very commonly used as a solvent in most reactions, because it doesn't react with things. All it does is dissolve things. It's got a little bit of polarity because of the oxygen. It's got a lot of non-polarity because of the carbons, and we now have a solvent. Fantastic. We'll end up using ethers all the time as our solvents. Okay. What happened in the bottom reaction? I said we had an elimination. I don't like this light. Not that light. Not that light. that not better?
I like the
Well,
Or you want them both off?
I like the
Now I can't see anything. What happened in that last one? We did an elimination reaction. How does that change our reactivity?
We added reactivity to a different type of reactivity.
What do you mean?
So now you have the pi bond.
Okay.
And so you could react that with something else.
So the pi bond can still act as a nucleophile. I agree. But you actually used an interesting word there. You added reactivity. Didn't the alcohol also act as a nucleophile?
But you have a better nucleophile.
I wouldn't go that far.
Reactivity.
But that's still not adding reactivity. You actually added reactivity here. What is that additional reactivity that we didn't have in the alcohol? When we have an alkene, where are those electrons in that pi bond? Both carbons, which means both carbons are now reactive. With the alcohol, I only had one potential site of reactivity for my carbons. The alkene, boom, 2. Okay? Some pretty drastic changes in how the structure can now potentially react. Yes?
I thought the alcohol had 3 spots with the carbon and oxygen.
It had one, so it had 3 sites of reactivity, only one carbon was reactive. Okay? Here we have one reactivity, it's a nucleophile, but 2 potential carbons. So we've increased carbon's reactivity, which is actually kind of cool because what have we got? We've got a carbon nucleophile. Oh, cool. That's actually one of the hardest things to do. With a carbon nucleophile, I can build larger structures. Without a carbon nucleophile, I can't really extend my carbon structure. So that's a pretty heavy reaction. Yeah?
I'm just trying to remember something we talked about last question. Could you use that? Is it called like a geminal halide?
So you're talking about geminal versus
I'm just trying to remember what.
vicinal? Seminal? Yeah, vicinal. For those who don't know me, guess what? When it comes to nomenclature, I'm glad Brian talked about it. Because I hate it with a passion. I think it is one of the most meaningless things to teach. Okay? But it is still a requirement. Okay? So I will still help you with it, but I am horrible when it comes to nomenclature. So if you throw out a fancy word, like I already told you to not make you use fancier words like vicinal or geminal, I have no clue what you're talking about. Okay? One of those means, and there's reference here, he's saying I'm making a dihalide. So where's our reactivity? At those 2 carbons. So I could put bromine on as a dihalide like that, or I could have put the bromine on as the dihalide like that. One of those is visceral, one of those is geminal.
Together.
That's what the textbook's for. Okay.
I was just trying to remember.
Between those, can you go from the alkene to the dihalides? Yes. Which one is easier to do? The first one I drew, yes, thank you for not adding the general distal into it. The first one I drew because both carbons reacted. Okay. And the second one, we added 2 bromines on, and we also had at the same time to add 2 hydrogens on. That can potentially change our reactivity. So depending on the reagents we're using, we may choose different choices or come up with different choices. Okay? Kind of makes sense? Okay. So that's our summary of our reagents. How do those reagents work? That now comes down to the mechanism. So let's see, do I actually simplify it nicely over here? Yeah, I do. What we're going to go through and do is activate our leaving group. In all of those cases, what did the OH have to do? Or most of those cases, what did the OH have to do? Leave. But what did Troy say about the ability of the OH to act as a leaving group? It sucks. So what does that mean? Make it not suck. Okay? To make it not suck, that oxygen needs to not be negative when it leaves. What could I put on there to make sure that oxygen is not negative? A hydrogen. Really readily available in, say, HCl, known as hydrochloric acid, hydroiodic acid, hydrobromic acid, acid, acid. Okay? So we're forcing that chemistry so that we can change the reactivity of our oxygen to make it a better leaving group. So what's happening in our mechanism? Okay, so now we've got our kind of hardcore review from first semester. We've got an acid now, HA, generic acid. I don't care what A is necessarily. What's our mechanism?
The lone pairs attack the hydrogen and the other hydrogen acid, or hydrogen, whatever acid is, bond. The electrons go to that one, making it negative, and
Yes.
the oxygen takes on the hydrogen.
Step one, all mechanisms, find electrons. Everything we're doing is finding electrons. We talked about finding nucleophiles, electrophiles, that's all we're doing. We're finding electrons. Where's the most obvious source of electrons? The lone pair on the oxygen. So that means the lone pair is always shown on the oxygen. No. Back second semester, we stopped drawing it almost altogether. You are expected to know that the lone pair is there because you passed first semester. Okay? So if you aren't used to seeing them, or if you see them start disappearing, start drawing them on. Okay? So we can find our source of electrons. Those electrons need to go someplace that is missing electrons. With that being A, it's kind of confusing, so we could switch that to, say, Br. Okay? What do we have now? HBr is hydrobromic acid. Why is it reactive? Because it's an acid. What makes it an acid? The hydrogen. What charge is that hydrogen? Positive. How many electrons does a positive hydrogen have? None. What does a positive hydrogen want? What did we find on the oxygen? Connect them. Okay. The repercussion of that single arrow, and this is another important aspect when drawing mechanisms. Okay. I'll get a lot of students potentially drawing something along these lines. So how many of you already jumped ahead and started to draw that out? Oh, okay. Well, that defeats that question. So there we go. We might draw that out. Is that correct? No. What's wrong with it? Okay. Oxygen has a positive charge. Okay. How do you know oxygen has a positive charge? Okay. A couple ways to approach this, primarily for the students that haven't had me. Okay. A little awkward with you, go back and forth, but it'll work. Okay. Formal charge. Every time you run a reaction, guess what you need to do? Calculate the formal charge on every single atom. This is what you should have done in first semester and should have been forced to do. I partially forced my former students to do this. Okay. You can talk to them, maybe they'll confirm or deny that. Okay. But you should calculate it every single freaking time because you get sick and tired of calculating it every single time, and you memorize certain patterns and know that when oxygen has 3 bonds, it is positively charged. You memorized it. Cool. Other way to do it is doing your formal charge calculation, which I can talk about later if you want. Okay. The other way to do it, what charge was the oxygen to start with? Neutral. Did you draw that? No, that was given to you, so it darn well better be correct. Okay? So if it is neutral, what is that arrow showing? Electrons. What are those electrons doing with respect to the oxygen? Leaving it. If our oxygen starts neutral and loses negative, what did it become? There it is. The arrows give you the answer. You don't even have to calculate formal charge. Okay? So looking at your structures and taking advantage of it. Okay? Is this now the correct answer? No. What's wrong with it? Okay, lone pair. Lone pairs aren't required, but good to show in. So let's add the lone pairs. We'll put them on the oxygen. We'll put them on the bromine. Is this now the correct answer? No. What's that?
We've got to show that the electrons are going to the bromine.
The arrow shown here and the answer provided. This is a super common mistake happening in second semester. You added the arrow to prove to yourself what's going to happen in the reaction. And then you said, I know what the answer is, so I'm going to draw the answer. Well, if you knew what the answer is, don't show your freaking work. You know the answer. Okay? Because it turns out, if I ask you to draw a mechanism, you're wrong. That is not what that arrow shows. What does that arrow show? I have a bond between hydrogen and bromine. I never broke the bond between the hydrogen and the bromine. Okay. Why is that important? Because it's getting you to take accountability for what you are drawing. You have to be perfect when drawing out your mechanisms. Okay, which sucks, but you've got to do it. Okay. Why is that a problem when we look at our now answer if we follow exactly what our arrow showed? Hydrogen can't exceed its octet. Which means that answer is wrong, which then means that's wrong. So what do we do to fix it? All we got to do is add an arrow. Sometimes it's as simple as adding an arrow. Sometimes it's as complicated as, oh crap, I'm completely wrong, restart. New arrow. Okay? And we now end up with our final answer. Now what do we have? We should have our correct answer, and we now have a new question. Okay, we started this whole problem off with two things and a reaction arrow. What do we now have? Two things and a reaction arrow. Do something with it. What do you see as reactivity within that? Bromine. What do you see on the bromine?
As a negative charge.
Negative charge. What do I need to stabilize that bromine? A positive. Where is there a positive?
There's a partial positive on the carbon.
Where is there a positive? I'm fishing for oxygen. So our natural response is, whoa, crap, I need to stabilize that, so let's give it to the oxygen. What's the problem with that? We'll end up exceeding the octet. Okay? So it's recognizing that our result has problems. So we can't share the electrons with the oxygen. We have to share those electrons with something else. Okay? Let's share it with the hydrogen. I think that's what I heard. I'm glad to hear that. What happens if I share the electrons with the hydrogen? You'll love your equilibrium arrows in second semester. Nearly everything we do in second semester has an equilibrium. If it reacts with the hydrogen, what happens? We go backwards. It's not that that's wrong, but we go backwards. Is there something else we could do that would take us in a more productive direction? We could have the oxygen take the electrons instead of from the hydrogen, from the carbon. That makes the carbon positive, which could then have the reactivity with our bromine. And we could end up with our result. Right? Everybody agree with the mechanism drawn? Anybody say, why did you do that? I don't believe you. Somebody had to have said, why'd you do that?
Why did do we have to get rid of the oxygen for the water first and then the bromine can come in?
So it's interesting. Is that what I did?
No.
No, I did it at the same time. What you're asking is, why didn't I just have water leave on its own and then have the bromine come in and attack? Well, it's a perfectly valid question. Okay. How would I decide between those?
Do both.
One option is to draw out both. See what the result is. What are we comparing when we look at those two?
Possibilities of rearranging.
Not even that.
Where the parts, if the positive is on a primary or secondary plate,
It's always going to be tertiary based on how this is drawn.
so then you know it's probably not going to be an SM2.
There's the word I'm fishing for. We're looking at a difference in mechanism. SN1 versus SN2. Are we going to get different results when we do SN1 versus SN2? Already started to hear. SN1 has a possibility for rearrangement. SN2 is backside attack, which means no rearrangement, which is the good thing. The bad thing, I get stereochemistry that I have to watch out for. Okay? How do I know which one's supposed to be which? This is where first semester and knowing your reagents. Okay? SN1 wants what kind of our substrate? Tertiary. What kind of substrate do I have with that alcohol? Tertiary. Is this mechanism correct? No. That is a tertiary substrate running under an SN2 mechanism, not an SN1. Okay. So that means what I've drawn isn't correct. So what we need to go through and do is break this into the individual steps, where we form our tertiary. That hydrogen's out there for a separate reaction. Now we can have the bromide come in and give us our final product. Once we've drawn our final product, we have to then watch out for some complications. We talked about rearrangements. There isn't one in this case, so we don't have to worry about the rearrangements. Last thing we should worry about, stereochemistry. Is stereochemistry an issue here? No. Okay, we do not have a stereocenter with that carbon, which means I don't have to worry about stereochemistry. We good? What happens if the structure changes? Do I then need to potentially worry about those other things? Yes. Okay. And this becomes one of the tricky things, is you tend to be in this habit of looking at the reactions and memorizing the reaction. When I take a cyclopentane and react it with HBr, I end up with bromocyclopentane. What am I going to throw on the exam? Tert-butyl bromide. Or not tert-butyl bromide. Let's do, can I do that one? Yeah. Tertiary butane. Oh, shit, that's not cyclopentane. Well, now I don't know what to do. Okay. Focus on the reagents and what functionalities are there, not the structure. Okay, so almost everything I draw is looking at generalized structures and pieces. Kind of makes sense? Yes?
Can you explain real quick why the carbon has a partial, does it have a partial positive charge because of the oxygen it's attached to? Is that
Yes.
why that, okay.
So why would the oxygen cause the carbon to be partially positive?
Because it's electronegative.
Bingo. And let's take it a step further than that. It's not just that oxygen's electronegative. It's what?
The octet's not full.
No, it still has its octet.
More electronegative than carbon.
It's more electronegative than carbon. It's what it's bound to. Because if I bonded it to another oxygen, it's not more electronegative than oxygen. Okay? So it's always a comparison. Make sense? Okay. So as we went through and did this, I decided to do it even more generically here. What is A minus? So we did the first step, said it was an acid. In the example we just did, we said A minus was a halogen, bromide. What is bromide? A nucleophile. What could happen? Substitution. What if it's not a halogen? What if it's not a nucleophile? Well, if I don't have a nucleophile, what am I then left with? If not substitution, elimination. So by looking and evaluating what that negatively charged species is, we can then start to predict something about where we go. Okay? Why would I go up? What happened in that up direction? What can you tell me about A minus? It is a nucleophile. You can give me more than that.
It's small enough to not be affected by the...
Why is the small important?
Because steric hindrance of the tertiary.
Keep going. Give me something about A,
Say it's like an OH group.
which is valid too.
Strong nucleophile.
It's a strong nucleophile. That's why I'm pushing in that upward direction, because I'm doing an SN2 mechanism. The only way the SN2 mechanism happens is if strong nucleophile. What happened in the bottom case? Okay, it's a weaker nucleophile, or there's a substrate effect coming into play, okay, which is allowing for the formation of the carbocation, which then puts us in this SN1 pathway. Okay, so in SN2, we're saying A is a nucleophile, and in particular, a strong nucleophile. When we move into the SN1 type pathway, we're now saying it's a weak nucleophile, or we have a substrate effect. Okay? A stable carbocation can form. Yes?
I was like, in this one, maybe this is where you're going, I don't know. Would you then, for that A minus, then act as a base? And remove that hydrogen?
Can A minus act as a base? What did we say HA was? A strong acid. The conjugate base of a strong acid is a weak base. Is that a good base? No. So this is an interesting feature of our alcohols. Cannot add bases. Bases aren't going to do you any good. Okay. And I did kind of forget about time. I just want to clear this out. Once we have that carbocation, we can then split again. Come on. And we can either do the substitution directly for it, or we could have done the elimination. So it's not necessarily SN1 giving us our carbocation. It is a unimolecular type reaction giving us the carbocation, which means SN1 or E1. Okay. We just covered a lot of kind of hardcore basics behind these reactions. We'll push through a lot more of the reagents on Monday. Thank you. Right? Because that's that next sequence, is just looking at all the different reagents.